Today, I have the pleasure to welcome François Pachet, who is now the new director of Sony Computer Science Lab. And François is going to talk about a topic, I think, which is very, very relevant to our robots, which is artificial creativity, with the particular twist of looking at this problem via Markov models and Markov constraints. So, François, I leave you the deck.
Thank you.
Thank you.
So yes, Jean-Christophe forced me to use this title, actually. Artificial creativity with Markov constraint. I don't think it means really anything for you. We'll try to explain why I think it makes sense to talk about artificial creativity on one side and constraints and Markov on the other side. So just a word, I'm at CSL. I also run a quite big project called Flow Machines, which this is why there is a website called Flow Machines, where most of what I say today is illustrated. There are papers, videos. There is a YouTube channel also, and many things like that. So I have to mention this because it provides a lot of funding for us. And the big project is about creativity. This word of creativity is very annoying because everyone talks about creativity all the time. There is a very funny cartoon. I don't think you can read from where you are. It's I think was in a New Yorker. It's a boss who yells at his employee, a bit like Jean-Christophe talks to you every day, and he say, "You get back to that goddamn cubicle, and start thinking outside the box. So please." Go back to your, small cell and be different. So it doesn't. Of course, it's very contradictory. It's very stupid. So we have a constant exhortation to be creative. It's very annoying. Yet the question of what is creativity is really interesting. Actually, scientifically, it's very interesting, and also in terms of the new application in a digital domain, it's very important to be able to say that a software creates something creative. When I say software, I mean a lot of possible things, which can be a composition software, it can be a robot. If you think about the robot as basically a software, it's important that you can say something about what is interesting that these things are doing, what is new, what is creative, and all that. So if you go to the site Flow Machines, I know I don't have a lot of time, so I'm going to just give you pointers. There is a nice video that tries to explain why we try to relate this issue of being creative to the problem of style. So I don't have the time to explain the whole story, basically, but more or less the idea that very often the creative things or creative people, they create something interesting by doing the following thing. They take a style, a way of doing that is already well known. For instance, Picasso was able to paint in the style of Velázquez very, very well. He was a very, very skilled painter. Paul McCartney and the Beatles were able to play music in the rock style, and they knew a lot of things also about the classical style. Actually, not them, but George Martin. But so what they did is that they would play, with the styles of whatever existed before. So if you are a musician, you play with music style. If you are a painter, so this is the famous story of Picasso's the invention of the bull by Picasso. So he would play around, use an existing style, and then add some ideas to that, and try to let's say bias the style in order to create something new. And sometimes it works, and this is, for instance, you can claim this is the way Picasso invented Cubism, is by taking the style of his predecessor and adding an idea. Well, let's do it with only simple lines, for instance. I'm caricaturing. It's just an example. Eleanor Rigby by the Beatles is the classical style, even the Baroque style of quartet, string quartet, with the constraints of pop music, with the meter of pop music, the harmonies in pop music. And so, very often, being creative, I'm not saying all the time, but very often in art at least, and maybe also in science, is you take a style, a way of doing in your model, and you can see this as a texture. For instance, you have a texture of a leopard, this thing on the left. So it's a texture, and the style is more or less the same. It's a way of doing. And then you take a structure, an idea of a global shape, for instance. which you can call a constraint. And then you put them together, and then you create something new. And indeed, what you see on the bottom, this kind of a rhino with a texture of leopard, is a new object. Is it an interesting object? This, I don't know. The context will say, the society will decide, okay? But what I'm saying is that very often the act of being creative consists exactly in mapping an existing style with a new set of constraints. And then playing around, fooling around with that. And sometimes create something new. And sometimes you create something new and you actually create a new style. And here you go, and the loop continues, if you want. And so my project, Flow Machines, and not only my project, but my vision of creativity from the viewpoint of let's say, engineers like you, computer scientists or scientists, is how to implement this plus operation here by a machine. And it turns out that it's very hard. Even for images, it's very hard. You know, there are not many people who work on texture in computer vision, but they're not able to do that. You can do things like that. You can approximate stuff, but you don't really know what is a structure, really. Try to tell a program that you want to build a house with a texture of a leopard. It's very hard to define what is a house, I mean, for a computer vision system. So what I'm trying to do here in this project is to do this in a very specific domain. First of all, discrete domain. I'm interested in creative artifacts that are sequences of stuff. You know, like in music, there's a sequence in time, an ordered collection of notes, of chords, of events, of stuff. Like text, which is also an ordered collection of whatever you want, words or letters or phonemes. Like a dance, you know, which can be a collection in time of movements, and a robot, if you want, who can, if you are interested in the way he moves, for instance, can be seen as a collection of, I don't know, basic movements or actions or whatever, a dialogue. So there are many, many things. Actually, a line, a sketch, you know, a painting, where you draw with lines is also a sequence, because a line is a sequence of sublines and all that. So there are many, many objects in which are sequential, and in which I'm trying to do this. Oops, sorry. So here I'm not the only one, the first one to do that. There is a very well-known guy called Markov. You probably know him because of Markov Chains, of Markov models, of hidden Markov models, and all this. And this guy, actually, I will say it later, he was also interested in creativity. He wanted to understand what is a creative text. You know, he was interested in Pushkin's poems, for instance, trying to understand from a statistical viewpoint what is really fundamentally different. And so by studying this, he invented this thing called a Markov chain, which is very popular, which is used absolutely everywhere in science, in economics, in mathematics, in Google ranking systems, for instance, in many areas. And the idea of a Markov process is really that you have a process that creates a sequence. Like one now, I have a process which creates words one after the other in time. And you want to model it. You want to have a model of this because you want to understand stuff about what is going to happen. You want to do prediction. You want to do analysis. You want to do if I'm going to continue doing always saying different things, or if after a while I repeat myself, if you have cycles, if you have ergodicity, if you have stuff like that. So you need a model. And the idea of Markov is extremely simple. It's almost a non-idea. It's to say, okay, if you want to model, for instance, a complex process that creates a sequence of what is called a state, or an observable state, you can make an hypothesis. If you consider that it is a Markov process, basically it consists in making the hypothesis that the probability of seeing the next event, given the current one, depends only on the current event, doesn't really depend on the past. Well, it doesn't depend at all on the past. So it's an hypothesis of amnesia, if you want. So the probability of having Si, what is Si? Yes, given S1 and S2 until Si minus 1, is actually the probability of having Si knowing only S minus 1. Why is this very interesting? Because if you say that this, if you assume this is true, then it's very, very simple to make a model of what is going on. This here is a very simple model of the global economy. And you can see it's very simple because you have only 3 states: recession, what we are probably now, bull market when the market is going up, and bear market, sorry, when it's going down. And here, So you have states and you have probabilities to go from one state to the other. So if you are, and you can go from one state to the same, of course, and you loop, or to the other. And from one given state, of course, the sum of probabilities must be equal to 1. It's stochastic. And what is remarkable here, it's simple. Why it is simple? Because here, when you are in whatever state, you can forget about how you got there. Okay. Okay, I don't have the time to say why this is interesting, but it's very powerful. Again, probably the most the well-known application of this today is a Google ranking system, which is based exactly on those kinds of ideas. And usually what you do now when you have such a model, if you don't want to do analysis, you can do also generation very easily by doing what is called a random walk. And random walk is just you take any state, any initial state, and then you draw at random dice according to the weighted, to the probabilities here, and then you do a transition according to the weighted, to the dice, the value of the dice. And according to those weights, and then you go from one state to another one, and you can repeat this, and you will create a sequence typically which will be which will look like, which will be very close to which look like, let's say, the sequences from the original model. So in that sense, Markov chains are also very much used for imitating style, and this has been going on for a long time, since the 60s. This is just to show that Markov was really not only a statistician but interested in creativity. So how does it work, and what is the relation with music and all that? So basically, the idea that you take, if you want to imitate the style. So remember, what I'm trying to do is implement my plus operation. I have a style of something, and I want to create new stuff in that style, plus some constraints. So this style is represented really usually like what we call a corpus, a set of sequences. All the melodies by Beyoncé, all I'm trying to find examples that young people can understand, but not me. All the Marcel Proust, I don't know any writer, Welbeck, okay, Michel Welbeck's books are sets of sequences of words. And so from this you do what is called estimation. You can try to build, for instance, the Markov model, which is, for instance, a matrix, a transition matrix, where you have all the probabilities to go from a word to another word, for instance. This is very easy to do just by counting. You can do more complex models, of course. And then when you have this, you can forget the corpus and generate new sequences by using dices. And this, the computational cost of this is 0, because you just go from state to state, and it's great. And if you do this, probably most of you have done that. If you do this on a text, if you do this on a sequence of notes, it works pretty well, And I will show you now, there are many videos of a system called Continuator, which I will not play, but I will show you what you can have when you do this on music. So here I have a Markov model that's going to be updated each time I'm going to play. So and you can hear it's not playing the same thing. It kind of sound like. I will play more. Each time I stop playing, he continues. This is why it's what's called a continuator. So you can recognize pitch patterns, rhythm patterns. Okay. I am very well known in the world as the worst GUI designer. I put buttons everywhere, by the way. I'm very proud of this. So you can see. So here there is a parameter which says forget. After a while there is a temporal window. Forget a bit, otherwise it keeps everything and it's kind of messy, So I'm trying to play other stuff like a. So you can recognize it as mixed up a little bit with the melodies before. So if I continue doing chord like and if I want, I don't remember, I can also loop indefinitely forever. And so here he's doing what? He's doing a random walk in a Markov model, estimated from whatever I've played here, and actually just the last bits, you know. And it's looping. So when it's finished, and we can wait a couple of years, suggest, just check that it's doing different stuff. Tell me when I stop. Okay, how to stop this? Here, you see the little icon? I emptied the memory, which means the Markov model is null, so it doesn't know what to do, it stops, okay? And I can, of course, do anything else, I don't know, like children stuff. Okay. Okay. Fine. I got a lot of success with this in the let's say the what you call this scientific community. Forget the name of this thing. Great videos, YouTube channel, Sony CSL Music Paris. Great. I will not show them. With children, fantastic. They can do incredible stuff. This was 10 years ago. And then we said, okay, let's do this serious. Let's try to push it really. Let's do really not what I've done there, like a demo, you know, to have fun, you know. Let's do serious things. And what does it mean, a serious things, you know? It means I want a random walk. Why? Because this is going to imitate the style. And I think you would agree that the system has imitated my strange style of playing. But it's not enough. If you compose music, if you write a text, if you are a robot and you want to do something, usually you have constraints. You have goals. There are stuff that you want to impose on the sequence you want to create. So if you are a composer, for instance, you want to create a piece of music, there are lots of things you want. For instance, if you are a jazz improviser, I have lots of nice videos here. You have to follow the harmony, you know, that is given by the tune, or you have to make sure that the last note is a good note, is a note of the chord. If you are in C major, it's nice to end by a C, for instance, or E or G, not a C sharp, you know, that kind of thing. So you have lots of constraints, properties that you want to enforce on the sequence. And the problem is that those properties violate all the time, most of the time, the Markov hypothesis. Because Markov tells you, okay, my model works, but you have to forget the past. And then you do random walk, it's cheap, it's great. Now I say, I want this, but I want also to have properties. I want the last note to be equal to the first note. How can you do that? You cannot. Many people have trouble understanding why it's difficult. Gabriele, who is here, maybe will help me convince you that it's difficult to do in general. But it's not only about I want the last note or I want the last word of my phrase to be a verb, you know. It's not only that. This is what we call unary constraints. But lots of other things, you know, that you want to enforce. For instance, you want to avoid, you want to have some diversity, you know. If you have a robot, okay, I'll try to take this metaphor, and the robot knows how to do basic movements. Turn on the right, on the left, whatever. You would like to avoid the robot to end up in a trap and doing only turning around himself all the time. You want him to explore, for instance. What does it mean? It means that you want a sequence where you don't have too much repetition. This is something you may want to do. In music, it's important. Actually, in music, it's important to have some repetition, but not too much. Okay? How can you be sure that your random walk is going to do that? No way to do that. And when I say no way, it's really impossible by definition. It's not an engineering problem. It's a basic problem. You want to avoid plagiarism. For instance, I have a Markov model of Michel Houellebecq's books. I want to create a new phrase. I don't want to copy the whole chapter. You know, otherwise, what's the point? I can as well copy the book. You know, so you want to ensure that your sequences are in the style, but that they are significatively different. Otherwise, it's plagiarism. How can you do that with a Markov model? Well, you cannot. You cannot absolutely. Well, there is one way you can. There is one way. Because it's so cheap, Markov models, you can do what is called generate and test. You know, you generate 1 billion sequences, and you look one after one, and you check. You know, keep only the sequences that verify your property. It's called generate and test. There is a problem with that, is that, and I don't have the time to explain in detail, but basically the problem is that when you enforce some constraint, when you say, I want the last node to be the same as the first one, I want the robot not to do more than 3 turns on the right, then the sequences that are solutions to the problem have a very low probability. So if you do generate and test, you will never reach them. This is a problem of sampling. It's very hard to sample in a space where a sequence of a very low probability. Actually, it's not very hard. It's just impossible. So you are dead. Meter. So in poetry, meter is about, I guess everyone is French here. Can I use one example in French? In French, we have poems which are called, based on a meter called alexandrines, 12 syllables. Le train ne peut partir que les portes fermées. 12 syllables. And with coupure à l'hémistiche, and then it's more than that, you have after a 6, le train ne peut partir, you have the end of a word. So it's actually 12, comment on dit les pieds? 12 beats, if you want, cut into, that you can cut into. Very hard to do with a Markov, well, completely impossible. In music, it's the same. You have durations. In music, this is a score. Even if you don't know much about music, if you are 4 bits, you have to have 4 bits, not 3 or 5, So 3, well, the problem is that 4 bits, you can do this with 1 note, with 2 notes, with 3, 4, 6, 8. There are lots of ways to have 4 bits. So you see it's very hard also to constrain Markov model to be to enforce meter. So in general, controlling a Markov model consists in enforcing properties that are absolutely impossible. If there is one message tonight, it's that one. It's impossible. And if you don't believe me, well, first ask Gabriele, and second, try to do it yourself. And then if you can, come and see us, and we will hire you. It's not possible. Okay, so what we have done is a new approach to generate Markov chains, this old thing, which is 1 century old, in which you can indeed generate chains according to a model and be sure that they satisfy a number of properties. I will go through the results and will try to be not too boring. The first result is a very general result that says basically that you can replace the problem of generating a Markov chain, which is traditionally seen as a functional problem. You generate one thing and then another thing which is a function of the last and so forth. And this is easy to implement. You can do this in 5 lines of whatever language. So you replace this by a problem in which you are going to actually search in the space of all the possible sequences you can generate. So if you have a Markov model of order 1, you want to generate a chain of length 10, a sequence of 10 basic movements for the robot, for instance. How many sequences do you have? Well, if you have 10 basic actions and you want to have a sequence of 10, you have 10 to the power of 10 sequences, okay, right? So 10 to the power of 10 is a lot. Already you could actually maybe try to see them all. But suppose you have 100 possible actions and you want to have a sequence of 2,000 micro actions. It's clearly not possible to do it in a very naive way. But this is still what we are trying to do. We are trying to explore the space of all the sequences using techniques that are known that can do this, let's say, fast. So the first result was about that. I will not explain how it works. Just say it's called constraint satisfaction programming. It's a very, very, very powerful technique to solve very quickly discrete combinatorial problems, like the magic square, Sudoku, all these things. With a constraint solver can be solved in no time. And so the trick here was to formulate Markov generation as a constraint satisfaction problem. What can I do with this? I will give you an example. Come back to my plus. Here I take a jazz composer called Charlie Parker. So he has composed a lot of blues, a lot of jazz blues, like Blues for Alice and many others. And this is my texture. I want to transform Charlie Parker in a kind of toothpaste, And I want to add a new constraint. I want all the chords in my blues to be different. This is why I put Boulet's picture. Boulet is a French composer who likes to compose music where all the notes are always different. It's very hard to listen to, actually. No comment. But I want to generate a piece of jazz in the style of Charlie Parker, who is a tonal composer, using this very crazy constraint. And I want the optimum, the one that has the highest probability, because I want a sequence that really sounds as much as possible as Charlie Parker while satisfying this crazy constraint. This is the result. And you have to listen that if you listen only any time 3 or 4 seconds, it sounds perfectly normal. But globally, it's crazy because all the chords are different, you can see, and you can see the probabilities. And since it starts, it's a blues in C, and it ends on G because G resolves to C, so this is completely normal. Start again. So you see, I mean, even if you don't know about jazz, I mean, there is nothing very surprising at any point in time, but the structure is very strange. So exactly, it's like the rhino with the leopard skin. So this is the kind of thing you can do with this technique. Unfortunately, you cannot do it in real time. It's a bit expensive. So there are other results. This one is a result that actually Gabriele contributed to, which is very surprising. If you come back to the problem of you want to generate a Markov chain, and then you want to impose what is called unary constraint. So you say at this point in time, I want this property. I want the last movement of the robot to be, to fall on the ground, for instance, and I want the 5th one to be a turn on the right, that kind of thing, you know. And I want the 10th one to be different from turning, anything but turning, you know. Unary constraint, and I want a sequence of movements of length, whatever. 10, 100. In the style of the robot, in the style of the robot's behavior, or in the style, if it's music, in whatever style. And it turns out that you can do this in real time with polynomial algorithm that gives you actually all the solutions in real time. I will try, if I can, to do a demo actually with music. So you have to be nice. So what I will do is I will play, I'm not sure it will work, but let's try. I will play very simple phrases. This is my corpus. You can imagine these are actions of the robot, you know. Stop. Stop. Okay, I will play another one, a phrase in C minor. Okay, now this is random walk, so I can have another one, I can have many others, and you can see that they all end on different notes. Now what I'm going to do is what I called here an answer. So the idea is I will do a phrase that will start by one note, go somewhere, and then I want a continuation so that the last note is my first note. Why I want to do that? Because it creates a kind of dialogue, musical, you know, like da ba da ba da da, and the guy say da 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 da. Okay, it comes back to me. So this is a unary constraint on the last note. Okay, I don't know if it works. I start by a C. Did you hear? It ends on a C. And I can have another one, and you can see the C is here, this thing. Can have another one, and also it ends on a C, as you can see. All of them. Okay? Now, so, okay, you can say, who cares? Well, yeah, it's very important. It means you can control a Markov chains with a guarantee of having all the solutions exactly with their probabilities. Only 5 minutes, I have to speed up. Okay, well, this once you have this, the research program was pretty clear. What else can we do? You know, so we can do a lot of stuff. We can do. So I skipped the technical part. How do you do that? There are lots of systems we build. You can do text with this. I want to mention because it's Gabriele's work and his PhD. You can do poetry. you take the Beatles here, the Beatles lyrics now, the sequence of words, yesterday all my troubles seem so far away. You take the rhythm, the prosody, the fact that the first word has a strong, weak, strong, yesterday prosody. This is automatically extracted. And then you take another style, Bob Dylan, and you keep the prosody. And you say, now I want to write yesterday by Bob Dylan. And you can check the innocence is yesterday, all my trouble seems so far away. And you can also impose rhymes and all that. So you can generate text. By the way, I think it's a very promising approach to text generation because you could see there is no semantics here. Yet you can generate very meaningful sentences most of the time. And you can control them. As far as I know, this is already like how much, 2 years old, 3 years old, maybe more. I've never seen anyone doing that. Many people do Markov generations. Many people do grammars, fluid construction grammars or other kinds. No one is able to do that because this is very hard to do. You have to explore the space of all possible sequences. Okay, I want to, another funny example. You take Winston Churchill, who said, I have nothing to offer but blood, toil, tears and sweat, which is not sweat and tears usually. And you say, okay, I want to keep the syntax of this phrase. I want to keep Winston Churchill's style. Winston Churchill has written a very, very big biography, memoirs. So you have a big corpus here. And you want to say, I want something that talks about France and business. And this is what you get. The French fashion to have but refuse business hours of effort. We didn't invent that. It's Churchill style plus the constraint that you want to have one word in there which talks about business, in that case business, and another one which is French. It's what we call a cardinality constraint. You see what you can do with style and constraint without any semantics. And of course, you can have all of them quickly. Okay. Meter is a strong result. I will not mention, sorry, I don't have the time. I want to talk about something else. Very nice result, which uses a very interesting theorem. I want to mention other applications. Harmonization. Very interesting. So you have a tune. This tune is a jazz tune called Giant Steps. Okay, the melody is very fast, ta, 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 and the chords are lots of different, very hard to play. And I take, and this is a constraint now, I take Wagner now, you know, Richard, and I take all the tetralogy, the opera, and I want to transform Wagner as a texture. And I want Wagner to harmonize this song. So you can see here, well, you will recognize, probably not very well, but you can try to recognize ta 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 ta, okay, with Wagner. So I don't have the time to explain how we do that, but the trick here is to use the melody as a constraint, as a complex constraint, but then let in the middle Wagner express his style by doing variations inside so that you can recognize Wagner. I mean, someone who knows Wagner would recognize Wagner here. And of course, you can do it with any style. We did it with Take 6, and there are examples on the web. I think I don't have the time. I played this to a very famous Brazilian composer in Rio. I played one of his big hits by my system. I can show you this video because it's great. And this guy is a very well-known composer in Brazil called Ivan Lins. He composed a song. Okay, I will take one more minute to do it. Very well-known, called Começar de Novo. Okay, very slow with a pattern like this which repeats all the time. And what I did, I generated a harmonization of his song by Take 6, who is a very well-known jazz vocal group harmonization, which is very hard to model with the system. And I played it to him. Now, this is what I played. I don't know what stops. Okay, and I played it to him just to show the reaction. So this is the composer of the thing, He knows Tech6. I'm going to play him a crappy MIDI file, you know, with this sound, and just to see his reaction to this thing. Okay, so it means he thinks it's great. Okay, in a few words. And to me, it's a better validation, of course, to do that than to do a demo or this kind of thing. I want to mention the last result. Can I? No, but so we'll. Thank you. We'll do it. Very important. This is very recent, a few months ago. When you use a Markov chain, whatever the field, you have a well-known problem which has never been addressed. Basically, it's called the order problem. So you remember I showed you take only the current state to look for the next one. Actually, you can take the two last states, and you call this order 2. You can take the n last states. You can order n. So in mathematics, there is no big deal, not big difference in there, but in practice, there is a big difference, because if you take the last n events or states, you will tend to generate sequences that are more similar to the corpus. And it was remarked already, it was observed by Markov and by many people a long time ago. The problem of that is that you have a tendency, so this is Markov order 1, you see, and the square, the colors. Okay, so you have colors that show you the bits, and they are all bits taken from the original corpus, and their length is like 1 or 2, you know. But if you increase the order, but the whole thing is actually copied verbatim from the corpus. Because if you take order 2, after these two words, there is only this word, you know. And after these two words, there is only this word. So you don't have any choice. You have to replicate. So what you do is indeed plagiarism. Well, you replicate a very, very big, although you are order 3, what we call the max order, that is the length of the largest chunk you replicate, can be very high, can be much more than 3. So we have, and this also is very hard to generate an order n, a Markov chain, by restricting the maximum order. So this is a result we had recently. There is a very nice web page on the web that shows you how it works. I just want to show you this slide. It's very interesting. So this slide tells you, okay, if you have an order 1 Markov chain, and you look at the distribution of the size of the chunks that are replicated from the corpus. So most of the chunks are of size 1. You know, some of them are size 2, and you have occasionally chunks of size 4, because you end up in a place where I didn't have any choice, you know, basically. But in terms of what you get, is we call this junk, because usually you will not, for instance, capture the syntax. You know, it's too low level, too low grain. So you increase the order. If you increase the order, then you will get chunks that are much higher. Here you can get chunks of length 4 with order 2, 4 up to even 12. And if you could increase again, you increase here to 4, Markov order 4 is not that much. You get mostly a lot of junk, and then and then a lot of things which are copied completely. You replicate the corpus. Okay, and so what is interesting is that what we are interested, creativity, remember, this was the subject of the talk, is something new, but interesting in the style. So here you have new things which are junk. Here, it's not junk at all, it's the corpus, it's replicated. So the sweet spot, you know, the interesting part is this one, where it's new, but not plagiar, but still in the style. The problem is with the Markov chain, if you play with the order, you will go directly from junk to plagiarism. Well, I mean, unless you are very lucky sometimes, you know. And so what we have done is a constraint that gives you exactly access to this. So you can exert a max order pressure. You can imagine, so you increase the order, the mean order, so you have something which is more similar to the corpus. And the max order, you prevent him from being doing a plagiarism. And you get exactly interesting sequences. And so you can apply this to music, to text. I think I have some examples here. Well, I will not show examples because Jean-Christophe is going to kill me. You go on the web, there is a maxOrder page that shows you example in text, examples in music, and here also you have the automata. You know, we have taken. Oh, here you are. So I know you don't see the colors still. Oh, I don't see the colors. Okay. So on the web you see the colors. Here there's the automata with no maxOrder. This is pretty homogeneous. As soon as you impose a maxOrder constraint, you can see structure appearing. You can see, you know, these dark things, a little bit like cancer on a radio, if you want. So you don't have this if you don't have any maxOrder. But if you put maxOrder, you have those islands. What are those islands? These are the things, the n-grams that are very, very connected to others. These are exactly the place where you have interesting stuff. Exactly. Now the problem that we have solved is how to compute them in a polynomial, let's say in a reasonably efficient way, which in this case actually is linear, which is a great success. Okay, and many other things, and we show you how you can generate music also like this by guaranteeing that the sequence you generate are new but still in the style. Conclusion. What I was trying to say that creative sequences very often can be obtained by taking a style, applying some new constraint, if possible a constraint that is different from the constraint that of the style itself, you know. If you do this, you want to compute it, it's a very hard combinatorial optimization problem, and actually it's actually a whole range of problems. And this is what we are trying to solve with this term Markov constraint, which is in fact a lot of different techniques for specific sub-problems. In the end, what we want to do is to say that the style, the way of doing of a robot, the way of composing of a composer, of writing, is this abstract thing which we call style, can be turned as in a computational object that you can manipulate. You can recreate something. You can add two styles. You can say I want the style of this guy minus the style of that guy, plus the style of all the English people or whatever. And so this is, I think, to me, a very interesting way to look at content, music, text, or even, I mean, robot behavior. Why not? I mean, you could imagine that the robot has a way of doing, has a style, in a sense, you know, statistical properties of its behavior in time, you know. And this is a very tool to capture that kind of thing. But then you want to generate new sequences with, again, which are different, not non-plagiaristic, which have properties, structural properties, unary meter, and so forth. And this is what we are able to do. I stop here. There is a website. There is a workshop in June where about text, specifically about what we can do with text and statistics, and how can we characterize creative text and all that. This workshop is in Paris 6 Jussieu in June, if you're interested. Gabriele knows about it. Sorry for being too long. Thank you. No time for questions anymore.